Welcome everyone. Today is the third day of the WOMANIUM Quantum Computing Program. We have an amazing speaker lined up for you. Marlo's going to kick off with introductions.
Good morning, good afternoon, good evening, everyone from all over the world. Welcome back to the Global Quantum Computing and Entrepreneurship Program. And it is my great pleasure to introduce our speaker, William Oliver. William Oliver is a quantum computing leader, building the fundamental technologies for quantum computing to make quantum computers scale. When he did his PhD at Stanford in 2003, the field was still emerging, still in its infancy. And since then, he has made the field grow. William Oliver is a jointly appointed professor of electrical engineering and computer science at MIT, a professor of physics, and Lincoln Laboratory Fellow at MIT, the Massachusetts Institute of Technology. He also serves as the director of the Center for Quantum Engineering and as associate director of the Research Laboratory of Electronics. His research interests span a broad range, mainly focused on superconducting qubits, where he is interested in the materials growth, fabrication, design, and measurement, and also the development of cryogenic packaging and control electronics. If you're not excited yet, next week on Wednesday, we will also have a virtual lab tour in his lab, where the dilution refrigerators that are needed to cool down devices to millikelvin temperatures are shown. Today, he will give introduction to quantum computing after having been a leader in developing this field for more than 20 years. William, please take it away.
Great. Thank you so much for that wonderful introduction. And it's really a pleasure to be here. Yeah, so I'm really pleased to be able to talk with you today about quantum computing and the introduction to it. Good. So before we get into quantum computing, I'd like to talk about the history of classical electronic computing. I think that's a good segue into quantum computing because it helps us to gauge how long this technology may take to develop. If we go back to 1906, the vacuum tube, a three-leg device, three-terminal device, was invented, and it was used primarily for radio receivers and transmitters for many years. Before we get into quantum computing, I'd like to give a review of the history of classical electronic computing, because I think that this helps us to frame how long this technology, a hard technology, will take. The vacuum tube, a three-terminal device, was invented back in 1906. It was used for many years for radio transceivers, but it was a good 40 years before we had a computer built from vacuum tube. You probably have heard of this, called ENIAC. That was in 1946, and it took up a whole room. You can see it here. Around that time, in 1947, the transistor, the bipolar junction transistor, was invented at Bell Labs. And within about 10 years, we had a fully transistor-based computer called TX0 or TIXO. That was in the mid-50s. And again, it's taking up a whole room, but it doesn't look anything like the computers that we have today. The computers we have today are based on chips, and this was just soldered transistors together. To get to chips, we needed the integrated circuit in the late 50s. But even with that, it wasn't until the 1970s that we started to see the types of integrated circuits that we today identify with computers. So for example, what I've showed here is the Intel 4004, a 4-bit processor. It had about 2,000 transistors. You'd have to fast forward into the 90s to get processors like the Pentium Pro with millions of transistors, and then another 20, 25 years to get to where we are today with multi-core processors, graphical processing units with multiple cores and billions of transistors. So from this vantage point, looking back, it's well over 100 years to get to this point. Now we can compare with that quantum computing. In the early 1980s, people like Richard Feynman and Uli Mannin and others proposed that if you want to simulate a quantum system, you should use a quantum system to do that, because it's hard on classical computers. And people thought about that. And in about 15 years, theorists started to come up with some of the foundational algorithms that we know of today. And one of the big ones, of course, is Peter Shor's factoring algorithm, which addresses cryptanalysis, adiabatic quantum computing, quantum annealing, Grover's algorithm. And at the same time, or around this time, the first ideas for how to do error correction, how to correct faulty qubits, also came to be. But these were just theoretical constructs. Now, in the early 2000s, Mike Chuang and collaborators factored 15. It was a demonstration of Shor's algorithm on a very small quantum computer. But you'd have to fast forward again 20 years to get to where we are now. And it's a very exciting time right now. We have quantum computers that you can access online. Now, they're very small, maybe 50 to 100 qubits at most, but you can access them and you can try out some of these algorithms. Not yet at a scale that's commercially relevant or viable, but at a small scale. And so the takeaway message is this. quantum computing is real. It's transitioning from what you might call laboratory or scientific curiosity to technical reality. That's happening around us all the time. But we need to recognize that advancing from a discovery to a useful machine takes time and it takes engineering. Maybe another takeaway is that you must be in the game to play. It's no surprise, I think, that many of the companies making these very fancy chips, technically advanced chips today, were in this field for decades. So with that as an introduction, let me present this outline. We'll start with quantum computing. What is it? I'll then talk a bit about my own research in superconducting qubits. We'll then talk about the path forward, and there's two topics there. One is engineering quantum systems, and just a slide or two on 3D integration. So first, how is a quantum computer different? Again, let's compare to classical computers that we're familiar with. A classical computer is based on a bit, for example, a transistor, and a bit is a classical bit of information. It's a 0 or a 1, that's it. These are discrete states, and these transistors are really, really good. They almost never have an error. The probability or the rate at which there's an error is better than 1 part in 10 to the 20th power. So if something fails, it's almost always the software, it's not the transistor. And what that means is that if I set the bit in state 1, I'll measure it as state 1. If I set it in 0, I'll measure it as a 0. Now, quantum computers are different. They are based on quantum versions of these bits, or qubits as we call it. And this can be any coherent two-level system. So there's still two states. We'll call them 0 and 1. We'll use this notation here. And the way to think about it is to use something called the Bloch sphere, or you can think about it as the planet Earth. So the planet Earth, there's the North Pole, and we'll call that state 0. And the South Pole, we'll call that state 1. And when you're at the North or South Pole, you're just a classical bit. That's it. But of course, we can be anywhere on the surface of the planet Earth. And when you're anywhere other than the North or South Pole, such as this point right here, you're in a superposition state of 0 and 1 simultaneously. Now, this is a manifestly quantum mechanical state. Doesn't exist like this in nature, at least classical nature that we observe. And if, for example, if you're on the equator, then you basically have an equal weighting of both 0 and 1 simultaneously. And so if you make a measurement randomly and probabilistically, half of the time you'll snap back to the North Pole, state 0, and half of the time you'll snap back to the South Pole, state 1. So, and that, even if you identically prepare yourself at the same place on the equator and make that measurement, whether you're going to project to 0 or 1 is random. And so that's clearly different. And quantum computers rely on this difference to encode and use information. And it's fundamentally different. So the implication can be seen here. A classical computer that has n transistors or n bits can form one n-bit state. So if n is equal to 3, there are an exponentially large number of states, 2 to the nth power. Since n is 3, that's just 8. So it's a simple case, 0, 0, 0, or 0, 0, 1, etc., all the way up to 1, 1, 1. So there's an exponentially large number of them, but we can only represent one of them at a time. And so if we want to calculate some input, let's say 0, 0, 0, we would put that into our classical computer, and it calculates some function of that and gives us an output. But if we wanted to run through all of them, for example, we really only have two choices. One is that we could sequentially in time put the different inputs into our computer, get an output, put the next one, get an output, etc. Or we could buy lots of copies of the hardware and do it all in parallel. But whether you do it in parallel via hardware or via time, it's an exponentially large number of states, so it's going to take exponential resources or exponential time. Now, a quantum computer, on the other hand, again, you can have n qubits, and now there are still 2 to the n, what I'll call components here, but we can put all of those components into a single superposition state with their own weighting coefficients, which we call probability amplitudes. So now there's one state, but it carries aspects of all 2 to the n components. And this leads to manifestly quantum mechanical effects called quantum parallelism, a quantum version of parallelism, and also quantum interference. And we'll get a little more insight into that in just a moment. So the question, though, is how do we take advantage of this quantum version of information, of encoding information? Well, it's not that different than classical computers. Classical computers run Boolean logic in an algorithm, and they do it based on a whole set of gates. Now, I'm not going to talk through all of these gates, but you're probably familiar with some of these, like the NOT gate, which takes an input and swaps it from 0 to 1 or 1 to 0, the AND gate, the OR gate, NAND gate, etc. There are many of these gates, and with just a handful of them, for example, the NOT gate and the AND gate together, or the NOT gate and the OR gate together, one can perform any Boolean logic algorithm. We would say that this is a universal set. It's not unique. You can pick different universal sets, but with a universal set of gates, you can perform any arbitrary Boolean logic. Now, quantum computers are similar. We have what we call single qubit gates, which are listed here. And basically, I'll show an example in a moment, but basically they're rotations around the planet Earth, single qubit gates. And also we have a couple of these, what we call 2 qubit gates. And I'll give an example of that in just a moment. But it's the same story. With just a handful of these single and 2 qubit gates, we can perform any arbitrary quantum logic. Now, in fact, we can use these gates also to implement any Boolean logic. But the reality is that often a quantum computer does no better, and in fact, often it would do worse, in running Boolean logic than a classical computer would do. But for certain problems, and we'll see a few in just a moment, a quantum computer can vastly outperform classical computers. And I should mention at this point that in almost all applications we foresee, quantum computers will be running in tandem with classical computers. So it's not that a quantum computer is going to replace a classical computer, but it can augment its performance. So let's take a look at what a single qubit operation looks like. What I'm showing here is the classical NOT gate. It takes an input and it flips it. So 0 goes to 1 and 1 goes to 0. The quantum version of that is an X gate. It takes quantum state 0 and turns it into quantum state 1. So what we're seeing here is, again, the planet Earth on the left, and on the right, as a function of time, is a pulse that we're applying to drive this transition. It's a control pulse. And what you see is a blue arrow pointed at the North Pole, which rotates to the South Pole under the action of this pulse that we're applying. And you can see the red arrow goes in and out along the x-axis. That's what we rotate around, and that's why we call it an X gate. So in this case, we're just going from the North Pole to the South Pole, and it's just a classical NOT gate. But we need not start there. We can start from anywhere on the surface of the planet Earth. And when we start anywhere other than North or South Pole, we start in a superposition state and we end in a superposition state. And to give some intuition, the action of the X gate takes these coefficients in front of 0 and 1, the alpha and beta, and it swaps them to beta 0 plus alpha 1. So this is just one example of a single qubit gate called the X gate. Now we can look at a 2 qubit gate called the control NOT gate, and its classical analog is the exclusive OR gate. Now, the exclusive OR gate has 2 inputs, X and Y, and we'll call X the control bit and Y the target bit. And here's the truth table. So we look at all 4 inputs. And the way to think about it is when the X control bit is in state 0, we just pass the value of the Y bit to the output. But when X is in state 1, we're going to swap the value of the Y. So 0 becomes 1 and 1 becomes 0. That's called the exclusive OR gate. So the quantum CNOT gate is the same, and we'll use a qubit X as our control qubit and a qubit Y as our target. And you can see the truth table is the same, only we're just using this notation now to indicate these are quantum states. And so what it means is that the rotation of the target qubit Y depends on the state of the control bit X. And we can use a very interesting example here as our input. We'll use an input where the control bit is in a superposition state of 0 and 1, and the target bit Y is in its what we would call its ground state 0. And the rules of linear algebra apply here, so we can take these one at a time. So let's first look at this one highlighted in blue. Since the control bit X is in state 0, we just pass to the output the Y value, which is also 0. So that's the term that appears here. And you can check that up here in the truth table if you want. But for this second term here, where the control bit is in 1, we know that we need to flip the Y bit, which we do here. And now what we see is that this is a very interesting output state, because we can't factor it into something that looks only like an X qubit and something that only looks like a Y qubit. They're fundamentally correlated, or as we say, they're fundamentally entangled. And so the CNOT gate that we show here is in fact called an entangling gate for this reason. So again, this is just another example, but with these 2 examples of single and 2 qubit gate, we can form a universal gate set on which we can perform any arbitrary quantum logic. So if we ask what an algorithm would then look like, it would look something like this. We have an input state where we have basically an equal superposition of all of our inputs in a quantum superposition. So these are components of a single superposition state that goes into the quantum computer. And then we start performing single and 2 qubit operations according to some prescription that the algorithm designer tells us. So the single qubit operations, for example. And what I want to emphasize here is that we apply 1 gate to 1 qubit, but you can see that it impacts every component in the superposition state. This is an example of quantum parallelism. This is followed by quantum interference, and the result is that the coefficients in front of these components, they change. Now, sometimes we're going to call for coupled qubit operations, where the state of one qubit determines what happens to the other one, like what we just saw. And that's followed by quantum interference. And the goal of an algorithm designer is that at the end of the algorithm, that all of the weighting is basically in front of one of these components. So that weighting goes to 1, and the weighting in front of all of the other components basically goes to 0. And that's because when we make a measurement, we will project out only one of these states. And the probability that we project it out goes as the magnitude squared of that coefficient. And so if that coefficient is close to 1, or ideally even 1, then with unit probability, we will get this result. And the 001 encodes the answer to the question that we're trying to answer. So that's basically how quantum algorithms work. And now you might ask, what are the ingredients to obtain a quantum advantage over a classical computer? Well, the first thing is there better not be a good, fast classical algorithm, because if there were, we should just use these computers we've got today. They're really, really good. The second is we need to, okay, we've got a problem. There's no fast classical algorithm. We need to have a fast quantum algorithm. And the third is that ideally it should be a useful problem. There are a number of problems where we have demonstrated that a quantum computer has advantage or can even be exponentially faster than a classical computer, but these may be for problems that aren't so useful or commercializable. So it's a very important intellectual step, but ideally we want to find problems that we really care about. So there's a small region today where there's useful quantum algorithms as we know it today, and there's a lot of research going into making that overlap bigger. And the types of quantum advantage that we can have are of two types. One is, and it's illustrated by this equation here. One is a polynomial in the number or size of the problem n, and the other is exponential in that size n. So let's take each one at a time. So if we can improve the prefactor, as we call it, this would be a polynomial improvement. And one example would be quadratic improvement, as we see from Grover's algorithm. So if n goes to square root of n, that is a polynomial improvement. Grover's algorithm being one example. More powerful, of course, is to reduce the exponent and reduce it from exponential to polynomial dependence. So for example, if you had a classical algorithm that runs in time, say 2 to the n, and we're able to, with a quantum computer, bring that n down to the first floor, n cubed, that's a substantial improvement. And we would say that that's an exponential improvement. Now, we don't see exponential growth in our everyday lives. And so to give an idea of that, you've probably heard of this, but let's just go through it anyways. Let's say your boss says, hey, I'll pay you one of two ways this month. Either I'll give you your salary of $1 million. It's a really good job. Or what I'll do is on day 1, I'll give you 2 pennies, 2 to the first power. And on day 2, I'll give you 2 pennies, I'll double it, so 2 to the second power. On day 3, 2 to the third. And on the 31st day, you can keep whatever number of pennies there are. And probably you could ask for 31 days, would you take the pennies? Or in fact, you just got a raise, it's $10 million now for this month. So what would you do? And most of us in our everyday lives don't experience exponential growth. So we think, okay, 8 pennies, 16, 32, 64. This isn't growing that fast. I think I'm going to take 10 million. But of course, if you did that, you would lose a lot of money because even just the 31st day, you're going to receive $21 million in pennies. It's a lot of pennies, but that's the power of exponential growth. To say it another way, if we wanted to simulate a quantum computer on our classical computers, we would need to store all of those coefficients that I was talking about. And if you had just 30 qubits, then you could do that simulation and store those coefficients on a laptop computer. If you went, though, to just 50 qubits, not even doubling it, now you need a supercomputer. One of the top 1 computers in the world. If you go to 80 qubits, now you would need the memory of all the computers on Earth. Double that to 160, and now we would need to use all of the silicon atoms on Earth, where each silicon atom is a memory element. And at 300, we're now talking about a number of coefficients that's all of the atoms in the known universe. So this is an example of exponential power, another way to look at it. So with this, we can look at quantum algorithms and speed up. What we have are a number of algorithms on the left, categories of algorithms. They're classical time and they're quantum time. And I won't read through the whole slide here, but what I want to emphasize is that these are the types of problems where we believe there can be quantum advantage. For example, simulation of quantum systems, quantum chemistry, factoring, that's Peter Shor's algorithm, finding solutions or sampling solutions to systems of linear equations, optimization, and of course, Grover's search algorithm. You can see the speed up here. Of course, there are still limitations. There's a lot of research that's still being done to understand how we can implement these algorithms and to do it in an efficient way. And I just show at the bottom here several professors here at MIT who fundamental ways contributed to these algorithms. So why don't we have a quantum computer right now? Well, it comes down to basically two timescales. And one is the coherence time. That's the qubit's lifetime. How long does it stay relevant, alive, and holding this quantum information? Now, at some time t equals 0, we can set the quantum computer into a known state, and we know it exactly, and we'll represent that state by the letter psi. But from that point forward, the quantum computer is interacting with its environment, whether it's the substrate in which the chip lives, whatever it is. So we're trying to implement these gates, but at the same time, the environment is implementing its own gates, if you want to think of it that way. And so over time, we begin to lose track of where the quantum computer is, and that state blurs and eventually is lost. Now, the qubits are still there. They didn't disappear, but the state that they're in is no longer known to us. And that time frame over which we lose the state is called the coherence time. Now, the gate time is the time required for a single gate operation, or a typical gate operation. And as you might imagine, the figure of merit is how many gates can I perform within the coherence time that I have. And I want to emphasize here that long coherence times alone are not sufficient. It's the number of gates you can do within that coherence time before an error. So we can compare different technologies against one another on this chart here. And I admit it's a little bit dated from 2019. On the horizontal axis is the speed with which we can run these gates. And on the vertical axis is this metric, the number of operations before an error. In benchmarking, we would call that fidelity. So one error in 100, we would say is a fidelity of 99%. One in 1,000 is 99.9%, et cetera. Now, to perform quantum error correction, the qubits need to, we aggregate qubits together, and I'll give you an example with a video later. Those qubits need to be at least so good if adding more makes things better, and that at least number, at least the more lenient values of it is around 99%. It depends on the type of quantum error correction, but one of the more lenient ones is around 99%. So you want to be above that line, and ideally you want to be in the upper right corner. So there are a number of technologies that are being used today for quantum computing, and I just show them here in terms of where they fall with 1 and 2 qubit gates. One of the leaders is trapped ions. I'm showing some folks here at MIT and Lincoln Lab working on that. Another one is my own research in superconducting qubits and some of my colleagues. And basically, you can see that they both have strengths and weaknesses. Trapped ions have really high single qubit fidelity, but they wish they were a little bit faster. And superconducting qubits, they're pretty fast, but we wish we had higher fidelity. And we're both working towards these goals. There are other technologies, for example, neutral atoms, nitrogen vacancy centers in diamond. Some folks working on that here as candidate technologies, as well as silicon quantum dots. And that's another area of research in my own group. So there's many technologies under development to realize the promise of quantum computing. And I just wish to mention that in the last few years, of course, there's been remarkable improvement across the board in order of magnitude or more, particularly in the 2 qubit gate on these technologies. So with that, let me now switch gears and talk about superconducting qubits. Superconducting qubits are basically quantum harmonic oscillators. A harmonic oscillator, in an electrical sense, is made by a parallel combination of an inductor and a capacitor. And you put them together, and when you do that, you have a harmonic oscillator. Harmonic refers to the fact that the potential energy profile of this circuit is in a parabola. Now, if we cool this circuit down to low temperatures, where low temperature means that the energy scale kT, Boltzmann's constant times temperature, is much less than the separation between these energy levels, which is basically Planck's constant times the resonance frequency, then this is a quantum circuit. And in fact, you will see discrete energy levels at this low temperature. But this is not so useful for a qubit because the pairs of energy levels, for example, 0 and 1, that separation is exactly the same as between 1 and 2 and 2 and 3. That's a property of a harmonic potential. So we can't uniquely identify 0 and 1 without driving all of those transitions. So the way we get around that is by introducing a nonlinear element. Could be the inductor, could be the capacitor. But with superconducting devices, we have a very natural nonlinear inductor called a Josephson junction. And what that is it's a tunnel junction between superconducting leads and an insulator. So a superconductor, in this case aluminum, is a material that when it's cooled down low enough temperature, it has no resistance. And the insulating barrier is aluminum oxide. So you can think of this as aluminum, aluminum oxide, and aluminum. And it's represented by this signal here, or the symbol here. And I won't get into the current and voltage relationship. These are called the Josephson relations that describe the current and voltage of this device. But if you combine them together in the usual way to define inductance, you will find that that inductance is nonlinear in the current that's flowing through the junction. So as a result, if I make this quantum oscillator using a junction inductor, which is nonlinear, and a capacitor, the potential profile changes. It's no longer harmonic. It's now, in fact, in this case, a cosine potential. And the consequence is that the frequency or the energy between 0 and 1 is unique and different from the 1-2 transition or other transitions. And so what this allows us to do is uniquely define the 0-1 transition. That's our qubit. So this is one of the simplest, if not the simplest, superconducting qubit. It's called a transmon, but a very large family of such superconducting qubits or artificial atoms can be built from this concept. And we can add additional inductors or capacitors or Josephson junctions to achieve certain properties in these artificial atoms that we want. So we can design the atoms we get. Now, I mentioned that it needs to be at a low temperature. And you could ask, well, how low? The answer is that it needs to be in the millikelvin regime. Part of that is by choice. We like this 0-1 transition frequency to be around 5 gigahertz because cell phone technologies and radar and other microwave technologies have been very well developed over the last several decades. And so there's a lot of equipment and know-how to actually drive and produce pulses at this frequency or this frequency range. It's not exactly 5 gigahertz. It's in that range, say 3 to 8. But 5 gigahertz, if you equate that to KT, has a temperature 250 millikelvin. And you want to be much colder than that. So we would like to operate at, say, 20 millikelvin. And to do that, you need a dilution refrigerator. That's what these pictures are showing here. To give a sense of scale, this plate is about 0.5 meter across and 0.5 meter down. Everything in this volume here, when it's closed up, is at 20 millikelvin. That's about 100 times colder than outer space background radiation, 2 Kelvin. So this is very, very cold, but you can still see many objects in here you might be familiar with, like filters, switches, attenuators, packages. And inside these packages, that's where the chips live that have the quantum processors and qubits. Now, another feature of superconducting qubits is that we manufacture them. So, and I want to emphasize that this is a silicon technology. We can use the same tool set that's used in a silicon foundry to deposit, etch, pattern, etc. these devices. What I'm showing here is a 200 millimeter wafer with lots and lots of qubits on it. If we zoom in on just one of those chips, you can see here's a chip with 5 qubits in a row. The plus sign here, that's actually a capacitor. And the inductor, where the junctions are, that's tiny, so we have to blow up this region here. And now you can see a loop, and there are 2 junctions. By putting a flux through this loop, we can actually tune the 0-1 transition frequency, a magnetic field. That's quite useful. And then if we zoom in on one of these junctions, this is what it looks like. And now we're down at the 100 to 200 nanometer size scale. Now, the other feature, as I mentioned, is that we use microwave control to implement those operations on the planet Earth or the block sphere. And it uses something which is common in electrical engineering and microwave engineering called I-Q mixing. This is a mixer. It has a local oscillator that comes in, and then we multiply that, the mixer multiplies, by another signal that comes from an arbitrary waveform generator. And when you multiply those together, you get this output pulse. Now, the important thing here is that this pulse is resonant with the qubit 0-1 transition frequency, and we can decide which axis we rotate around by deciding whether we use the I port or the Q port. Here's how it works. The planet Earth over on the left, again, the blue vector here represents the qubit state. We are now using the Q port, and the Q port rotates around the y-axis. And so we'll do this one more time. So we're going to start with the I port, or an X gate, and that rotates 180 degrees. If we invert the amplitude, we now rotate around minus X. We'll now switch to the Q port, and that rotates around the y-axis. If we use a smaller pulse with half the area, we can go half the distance to the equator and then back up to the North Pole. So this is how we can drive our qubits. And when we do that, we need to do it with very high fidelity, as I mentioned before. And I just show some data here. I won't go into detail on it, but for all of the different types of single qubit gates, whether it's a pi pulse or pi over 2 pulse or Z pulse, what we find in our group is we have more than 3 nines, as we call it, fidelity, because there are 3 nines and then some other number. And that would be 99.9x% fidelity on the single qubit gates. For the 2 qubit gates, there are 2 primary types. One is called an I-swap gate, and one is called a controlled Z-gate. We looked at an example of that one. And you can see here that in our group, we're almost at 99.9%, here almost at 99.8% for these two types of gates. And if you'd like to learn more about those experiments, please take a look down here. Finally, one reason superconducting qubits have advanced to the degree they have over the past 15, 20 years is because of a remarkable improvement in their coherence times. The first qubit in 1999 by Nakamura and colleagues at NEC, it was about a nanosecond. And since then, we've improved to over 100 microseconds. I just list here some of the times for the different types of qubits we have. And this remarkable improvement is due to groups worldwide, and it's improvements in materials fabrication and design. Here are a few review papers if you would like to learn more. And based on that, where we are today, this is basically what processors look like, quantum computing processors that you can access in the cloud. So here's IBM's Eagle processor in the lower left, Google's Sycamore processor. Here's a processor from Rigetti. These are all superconducting gate model. Here's IonQ's trapped ion quantum computer. And here is a D-Wave quantum computer, which does a different type of computing called quantum annealing. Now, of course, here in the middle, this is not a quantum computer. This is obviously an airplane. It's the Wright Flyer. It was the first airplane that was self-propelled, had a person on board driving it. I think I like to put this picture here because I think this is roughly the state of where we are today. This was a tremendous technical achievement at the time, and all of these processors here are tremendous technical achievements in their own right. But we know that it was going to take a while from the Wright Flyer until we had airplanes that people could board and take a vacation. So it's going to be a while, but nonetheless, this was a tremendous milestone at the time. And basically the question is, how are we going to go from where we are now to realize the promise of quantum computing? And the answer is that we now need to do the hard work of engineering quantum systems that are robust, reproducible, and extensible. Now, one experiment that you may have heard of is Google's quantum advantage demonstration from 2019. And what I want to emphasize here is that they had a quantum chip. This is Sycamore. It had 53 qubits. I don't have time to go into too much detail on the experiment itself, but what I want to emphasize is that what they did is they increased the number of qubits and performed a random number generator experiment with they've generated a random number, put on random gates, saw what came out. And then they asked, if we wanted to simulate that on a classical computer, how hard would it be? And eventually they got into a regime where they really couldn't, in practical time, do that simulation. And that was a very important demonstration of quantum advantage. Now, again, I think it's still very early. In the news and views piece that I wrote, I said, hey, this is a lot like the Wright Flyer. It's important. Now let's get to work and make commercially viable algorithms. But what's interesting about this is that with 53 qubits of the transmon type, the Google Quantum AI team demonstrated a calculation in about 200 seconds that was expected to take a few days or more on the Summit supercomputer, which at that time was the #1 supercomputer in the world. I think today it's number 2. The Summit supercomputer, by the way, has 40,000 processors. It has 10 to the 17 transistors. It has 10 to the 17 bits of memory, and it uses hundreds of megawatts to do that calculation, whereas on this chip probably took about 100 kilowatts. So there's lots of ways that we can look at quantum computers and their quantum advantage. It's not just speed up. So just a few words on where we're going from here to engineer quantum systems. And what I'd like to talk about here is that the architecture of a quantum computer looks a lot like the architecture of a classical computer. You have an interface at the top where we write programs. There's going to be a logical controller that interprets that and then tells the physical qubits what to do. In between, we have some layers of error suppression, and we'll talk about that in a moment. But on every clock cycle, what's happening in a quantum computer is that, of course, we're implementing those single and 2 qubit gates to do the algorithm, but we're also looking for errors and suppressing them. To give an idea of how this works, I like to use the example of lacrosse. And so we'll now look at a couple of videos about lacrosse. The physical qubits themselves are faulty because of the noise in their environment. And that's represented by this young man right here, who's carrying a ball on his lacrosse stick, but he's going to do it in the wrong way. He's very unhappy when I asked him to do this, because as he's running across the ground, he just tries to hold the ball in the stick. And of course, the noise of him running and the bumpiness of the ground means the ball is going to fall out almost immediately. And that is just like the physical qubits in their environment, which is noisy, losing quantum information. So of course, we don't play lacrosse that way, nor do we operate our qubits that way. What we do is something called passive error suppression. When you play lacrosse, you cradle the ball back and forth like you see here. You don't think about it, you just do it all the time. And what that does is it decouples the noise of this boy running from the ball, or it decouples the ball from the noise, and so the ball stays in the basket, and then he can go down and score a goal. So this is an example of passive error suppression. Passive because he's not feeding back anything. He's just cradling, as they call it, the stick back and forth. But that's enough to decouple from many types of errors, but not all errors. And we know in lacrosse, for example, another type of error that can occur is that the defender comes up behind you and just knocks the ball out, even if you're cradling. And when that happens, you've got no choice but to first identify that the error occurred, find out where the ball is, and then fix the error, pick it back up. And that's exactly what we do in quantum computers with quantum error correction. We identify that errors occur, when they occur and where, the type of error, and then we go in and fix it. And what's magic, I would say, or not magic, of course, but fascinating to me about quantum error correction is you can do that without losing the quantum information. Just a couple more slides. I know we're coming to the end of the hour. So we've seen this picture before. This is 5 qubits in a linear chain. Here are some look at data. We saw some of this 1 qubit and 2 qubit fidelity numbers before. These oscillations are called Ramsey. But of course, we don't want to stick with linear chains. Of course, we want to go to 2D arrays of qubits and to go to larger numbers. And what you're seeing here is a 16 qubit chip from the Equus group at MIT. And what you notice is it's getting pretty crowded. There's a lot of lines that are trying to come in to control these qubits. And in fact, it's so crowded that occasionally we have to take long wire bonds, which have not good microwave properties. So you ideally don't want to do that. We know that this is not the way that we're going to extend and go to larger numbers of qubits. We can't do that in 2 dimensions laterally. We have to go into the 3rd dimension. And so what you're seeing here is a refrigerator that we're installing at MIT through a generous donation from Keysight Technologies that will be capable of measuring up to 64 qubits at a time. But if we wanted to put a 64 qubit chip in there, we can't do it this way. It's just not going to work. And what we need to do is to break the plane, so to speak, and start bringing in the control wiring from the 3rd dimension. And so to do that, we've developed at MIT and Lincoln Lab what we call a 3-stack, 3D integration with 3 chips. We call it 3-stack. The qubit chip is on top, but face down. There's a middle chip here, which we call an interposer, and has through silicon vias. And then at the bottom is a multi-wiring layer, readout and interconnect. And by multi-wiring layer, what it means is that you can have wires going over and under each other without shorting. You get the signals where they need to go under the qubit, and then you bring them up to talk to the qubit. Now, some features of this is that the interposer and the qubit chip are very similar. So the qubits retain their high coherence, we would say an isolated mode volume. We get another surface where we can put active elements like qubits or couplers. And of course, what makes this possible is the advent of through silicon vias. And I won't have time to go into more detail on that today, unfortunately, but we have a lot of publications in this area, and I'd encourage you to take a look. Last slide. Quantum computing development started out largely as a computer science and a physics discipline. But as we transition to real systems, what we realize is that the diversity of talent that we needs to get much, much broader. And we've coined this as quantum engineering. To my mind, what quantum engineering is it's a bridge. And it's a bridge between what you would call the School of Science, if you're at a university, or science and mathematics. And it bridges that with the School of Engineering and their disciplines. People on both sides, the classical engineering side and the science and the math side, they both have to pivot to address the problems that we have in building quantum test beds so that we can realize future quantum systems. And so this new discipline, which we're calling quantum engineering, I believe is the bridge that connects these. And it really takes almost every department at a university has something to contribute to the goal of building quantum systems of the future. And so with that, let me thank you for your attention and also acknowledge the many people on the team, both at Lincoln Laboratory and the MIT Engineering Quantum Systems Group, who've contributed to this work and are many sponsors. And these folks are really the ones who make it happen. And so with that, let me again thank you for your attention.
Thank you very much, William Oliver, for this wonderful presentation with very intriguing numbers that excite everyone, I think, telling that 300 qubits would be equivalent to all atoms in the world, and then diving deeper into the physics and outcomes of superconducting qubits. There are many questions in our Discord. Some have already been answered during your talk, and wow, they are still popping up. Thank you all so much for your active participation. We will get started with questions. One of the questions is, you have been talking about superconducting qubits. Are there also attempts to realize a 3-level system? Or is there a reason, apart from technical realization, why 2-level systems are preferred? By Johanna from Germany.
Yeah, thanks. That's a great question, Johanna. In fact, one can use three-level systems, and researchers are looking at those as well. And that's true for qubits. It's also true for classical logic. One could use three levels there as well. Now, in the case of quantum computing, three levels gives you more states. And so in principle, the number of qubits one would need to run a problem might be less if you can use three levels. Sorry, I called it a qubit, but it's actually called a qubit if there are three levels. And in fact, you could have more. They call that a qubit for 4 or more, where D represents the number of levels. But the issue is that the advantage, of course, you have more ability to encode in each physical qubit. You can encode more information, or there are more states to use therein. But the disadvantage is that the coherence times may suffer, because now there are more channels by which that qubit can relax, say, to its ground state. So in a qubit case, of course, state 1 could relax to 0, but state 2 could relax to 1, and in some cases, maybe even 2 to 0 directly. So it's a no free lunch principle at work, where there's some advantages by adding the complexity, but there's a trade-off with some disadvantages. What I think is exciting about quantum computing today is that we're at the point where we have lots of options available to us, and we can now do a systems analysis and ask, for the thing I'm trying to do, what is the best path forward? Should I use a qubit? Should I use a qubit? I think that's immensely exciting.
Thank you very much. Then there were early questions about, for a typical computer, the basic unit is a transistor. What is the basic unit for a quantum computer? It was followed up by how are gates applied to qubits in real setups. And then we learned about how that is done for superconducting qubits. People already commented, this depends on physical realizations, which types. Could you briefly comment on that? We will have more lectures about that next week, but a brief insight into that.
Oh, into the different ways that we can control qubits for different technologies? Is that the question?
Yes.
Yes. Okay, very good. So it depends on the type of qubit, as you'd imagine. So some of them are controlled by microwave pulses, like superconducting qubits can be controlled that way. Semiconductor qubits can be controlled that way. Some of the natural atoms, like neutral atoms or trapped ions, they can be controlled. They typically are controlled by laser pulses. So still pulses of electromagnetic radiation, but now in the optical regime rather than in the microwave regime. So the concepts are similar, but just a very different frequency. I should mention that some of those atoms can also be operated in the microwave regime. So it's not one or the other. There's some choice there. And then what I talked about today was primarily what we call resonant driving, where you use the 0-1 frequency value, the transition frequency, and that's the frequency of the pulse you apply. But that need not be the case. Sometimes we do non-resonant driving as well. So there's really a large number of ways to do this. But I would say, in a nutshell, we're either doing microwave pulsing or optical pulsing.
Great. Then Fabrice Benoit from the US pointed out cleverly about your graphs. If 2019 is dated, then what is the current rate of decoherence? And I would like to couple that to another question. Is there a fundamental limit to gate time for each hardware implementation? And you talked about both times.
Yeah. Thanks for that question. That's spot on. So I tried to indicate with those red arrows that the fidelities have improved at least an order of magnitude in the last two and a half years. So progress continues to be very fast. The specific coherence time depends on the technology. Now, some qubits, like superconducting qubits, the coherence times are in the hundreds of microseconds, even a millisecond on the research side. If you look at some of these neutral atoms or trapped ions, those times can be extremely long. Even in some cases, unmeasurably long. Now, as I mentioned, long coherence times aren't enough. Generally, it's good, but what also matters is how long it takes to implement a gate. And for those very long-lived technologies, typically their gates are much slower as well. And so the net fidelity that one gets, and that's what really matters, is what's the fidelity of my gate, typically aren't that different today. That people are getting 99.9 or 99.99% single qubit gate fidelities, maybe a little better in some research cases, but that's true whether you're talking about superconducting qubits or, say, trapped ion qubits. And one other just small note to make is that it's not only coherence that matters. There are some cases where the coherence times are just really, really long, but there's noise or imperfections in the control, and that can also cause errors.
Thank you very much. There are more questions specifically about superconducting qubits. In view of time, I would like to bring those questions to next week when Daniela Bogarin from IBM program will talk much more about superconducting qubits. And I would like to thank you very much, William Oliver, for this fantastic talk, this fantastic introduction to quantum computing.
Yeah, thank you very much again for the invitation. I really enjoyed it.
Thank you. And let me read some comments from the people. They say, amazing talk. It was great. So inspiring. Wonderful lecture. Thank you very much.
William, nice to meet you.
Yeah, you
Quickly,
too.
just-
Well, fantastic. It's good work and interesting topics. So glad that you're doing this.
Thank you. Yes, I'm excited to work with US government agencies like the NIH in computational neuroscience, NASA, so the James Webb. Our team did some of the safety testing when it was at Goddard. So, and all exciting technologies.
Good, good. Well,
Okay.
that sounds great. So this is just one of many.
Well, we hope to do this every year. So I hope you come back again next year
Oh, of
and keep
course.
sharing your wisdom.
Of course, until you get tired of me. Oh, great. Thank you. Yeah, this is really fun and really appreciate the invitation to speak.
So, William, I'm not sure how much Malu has shared, but you may have seen the demographics document that she may have shared as well.
Yep.
We have students from about 50 different countries right now, 3% of them from MIT. So we know we're doing something right if we can teach something to MIT kids. Another 3% from Caltech, so they're not far behind. Stanford, Yale, pretty heavily represented. We reached out to the quantum computing associations from different colleges as well. So UT Austin, Texas. And then we have students from Germany, which you would expect, from India, which you would expect, and a lot from Mexico, which I don't know if you would have guessed, Indonesia, Cameroon, and all from the top technical universities in those countries. So incredibly diverse. About 30% are PhD students looking to make the switch to industry. And then I think the rest, like 30%, 10% postdocs, 30% undergrads, 30% masters.
Fantastic. Yeah, that's wonderful. Yeah, really good news. Yeah, we need, particularly in this field of quantum, we need more and more people, professional development and quantum engineers, people to go into industry. There's so many job openings right now, and companies just have so much trouble filling those positions, right? It's natural, I think, that this transition that we're having now from the more physics-based education to something that's much broader, there's this transition period that's difficult, right? We need to get more people in the pipeline, and also people who are already in industry, allow them to pivot to this new field. And we've developed some courses at MIT specifically targeting both of those groups, one for the professionals already in industry, and then now for students.
Great, that makes a lot of sense. Yeah, maybe we should think of doing an education program a bit long term. For us, it's like we are not here to replace university, right? Our goal is to excite students and give them a little bit of exposure to the cutting edge, and then have them be on their own journeys. So many of them, they continue obviously with their university education, but for us, it's that simple exposure sometimes that can change someone's trajectory. So how we can kind of, people as they advance through these programs as well, right? Send them to you, send them to other places would be a good question.
Yeah, no, I think that's an important part of the whole process. And, it's just stunning what reach these companies can have. And it's fun. I think students really love teaching other students. And
what does it take to get into a place like MIT or maybe even industry? Like, is there like a valley of death, you think, where there's a gap in education that's not being filled right now?
Well, getting in at the undergraduate level, I think, is as it's often been in the past, where it's a broader education that I think we look for. But nonetheless, exposure like this program, these are things that a student can say, hey, in their statement, this affected my trajectory, and I really want to study this in college. And of course, they need the credentials to get into college, but this certainly helps, and helps them hopefully choose, or gets them excited. That's the most important thing. I mean, they'll choose whatever they want to choose in the future, but just getting excited about science is the most important thing, I think. If we accomplish that, good.
Yes, quite agreed. Raj, do you want to say hello as well? Quickly introduce yourself if you're there.
Good morning, everyone. My name is Raj from WOMANIUM. It is great
Raj.
to meet you all. Hello, William.
How you doing?
Great to meet you.
Good to meet you too.
So Raj used to be at MIT in the media lab as well. I'll introduce him. And then he got pulled by his professor to work under President Obama when she was made CTO. So yeah, when she was made CTO, Raj joined as well. So he worked under President Obama in the OSTP office, which is the Office of Science Technology Policy, for a number of years. And then after that, he got a promotion and joined WOMANIUM. So
All right, fantastic. Sounds good. I also I did my master's degree in the MIT Media Lab way back when. Sounds like a Media Lab reunion here.